In this video, I am going to talk about the theory behind homogeneous differential equations. However, I want to introduce the concept not with theory directly, but with an example. So let's consider this differential equation. So here is an example. dy over dx is equal to y over x plus, let's say, y square over x square. This is a differential equation that we kind of cannot solve with the techniques that we know. First order linear differential equation. So there's going to be dy over dx plus p of x times y is equal to q of x. I can't express this in this format, nor can I express it in this format. Dy over dx is equal to, let's say, f of y times g of x. So this equation, at least I don't know of a way to convert this into either this format or this format. So how do we go about solving this type of differential equation? As it turns out that there is a way to do it if you do a substitution. So let's go ahead and make a substitution. Let's say v is equal to y over x. Okay. Then my y becomes v of x, v times x. Then I could take the derivative of y with respect to x and then use the product rule, d over dx v times x. That I could rewrite as v times derivative of x, which is just 1, plus x times derivative of v. Now remember, v is a function of x and y, so I just leave it as it is. So dv over dx. Now this is actually my dy over dx, which is this. So now what I'm going to do, I'm going to do some substitutions. So I'm going to replace this dy over dx by v plus x times dv over dx. So please note, dy over dx is equal to this. Now on the right hand side, I made the assumption that v is y over x. So this is going to be just v plus y square over x square is going to be just v square. Now you kind of probably see that this equation, this differential equation, by making a substitution, I have converted it into a separable equation. Let's show it to you. Subtract v from both sides. Then you're going to get x dv over dx is equal to v square. Now if I rewrite it, this is going to be dv over v square is equal to dx over x. Now I could go ahead and integrate both sides of this equation. If I integrate it, on the left hand side, you're going to get negative 1 over v if you simplify it, because it's going to be v to the power negative 2 plus 1 divided by negative 2 plus 1, which is negative 1 over v. And on the right hand side is going to be integral dx over x, which is nothing but ln of x, right? You can put absolute value of x, or you should put absolute value of x plus some arbitrary constant c. Now I can go ahead and rewrite it, and it's going to be negative 1 divided by v is, by the way, what is it? Y over x. So it's going to be y over x is equal to ln of absolute value of x plus c, or negative x over y is equal to ln of absolute value of x plus c. And if I solve for y is going to be y of x is equal to negative x over ln of absolute value of x plus c. So this, by the way, is my solution to this differential equation. As you can see from this example, we have made a substitution, which is v is equal to y over x, and that substitution converted this equation into a separable equation, which is right here. And we know how to solve a separable equations, and we just use the techniques of separation, and then we solved it. Now, this is an interesting way of solving a differential equation that we cannot solve with our usual techniques, like integrating factor or separation of variables. However, we can make a substitution and convert it into an equation that we can solve. In this case, separation of variables. So let's go ahead and kind of generalize this concept. If we look at this equation, we notice that dy over dx is equal to y over x plus y square over x square. This is, by the way, I could write it as a function of y over x. You can think of y over x as an input, just as one input going into this function. So this is in essence a function of y over x. So if you have a differential equation that could be written in this format, dy over dx is equal to f of y over x, that differential equation is called a homogeneous differential equation. Okay? If you have a differential equation that could be written in the format dy over dx is equal to f of y over x, it is called a homogeneous differential equation. So it's homogeneous. Differential equation. Now, this is one definition or one version of the homogeneous differential equation definition. There is another way you can define it too. And that definition has this format. So let's say m of x comma y dx plus n of x comma y dy is equal to 0. A differential equation of this format is called homogeneous if both m and n are functions that are homogeneous. If both m and n are homogeneous functions of the same order or degree, okay, same degree. Yet there is another variation of this thing. So some people write it as dy over dx is equal to m of x comma y divided by n of x comma y. It's a differential equation that is homogeneous, or it's a homogeneous differential equation if both m and n are homogeneous functions of same degree. Okay, so this is just another way of writing it. However, let me kind of briefly define what a homogeneous function is. So let's say we have a function f of x comma y. I will stick to two variables. It could be easily extended to n variables, and it could be also extended to vector functions as well. But for the sake of argument and simplicity and relevance, let me go ahead and do it for two variables. This function is called homogeneous. Homogeneous if, let's say some number t, and t is not equal to 0, okay? T is not equal to 0. If I replace x and y by tx and ty, okay, ty, then the outcome is going to be t to the power some number k times f of x comma y. Okay, if you can do this for any function, it is called a homogeneous function. Now let me just give you a simple example, easy example of two functions where one is homogeneous, the other isn't. So let's say f of x comma y is equal to, let's use easy one, x squared plus y squared. So then in that case, my f of, let's say 3x, let's say t is 3, and 3y is gonna be what? 3x whole square plus 3y whole square, which is of course 9x square plus 9y square, or 9 times x square plus y square. That is the same as 3 square times x square plus y square. Do you see that the degree here is 2? Okay, this k is equal to 2 and t was 3. So this is a function that is homogeneous, whereas this function is not a homogeneous function. So f of x comma y is equal to x square plus, again, y square. Let's add something like a 2. Okay, so f of 3x 3y is equal to, again, 9x square plus 9y square plus 2. If you factor out 9, you're gonna get x square plus y square plus 2 over 9. However, this is not equal to f of xy, right? This is not equal to f of xy, which is x square plus y square plus 2. Therefore, this is not a homogeneous function. So let's go back to our differential equation. So this is my differential equation, dy over dx, okay, is equal to m of xy divided by n of xy. Now if m has the same m is a homogeneous function, and n is a homogeneous function of the same order, then this differential equation would be called a homogeneous differential equation, which, by the way, kind of tells you this is kind of this, right? So another way of defining the same thing is, or a function, a differential equation to be homogeneous is to have this structure where you can write the differential equation as a function of y over x. Then you can do the substitution and you can go ahead and solve the differential equation by converting it into a separable equation, okay, which is here. And I have shown you how to do this process, this substitution, as well as solve the differential equation through this example. I hope that this discussion was helpful. Thank you very much.